Hi folks, welcome back to 5.1 part 4. So we've talked a lot about area, if we can find exact area, and then we talked about what happens if we had to approximate the area. And so now we're going to see how can we tell if it's going to be an overestimate or an underestimate, or which one might give you an exactly perfect one, okay? So let's start with question number 5. We've got a few different parts going on here. So let me zoom in a little bit. We have a lower bound or starting point of 0. We have an upper bound or an ending point of 2. And the graph that we are interested in drawing is the graph of x. And so if I want to make a quick table for a graph of x, so 0, 0.5, 1, 1.5, and 2, I get 0, 0.5, 1, 1.5, and 2. And that's just because whatever I put in for x is what I'm going to get out for y. So I'm going to go ahead and graph that. So I've got 0, 0, 0.5, 0.5, 1, 1, oops, 1.5, 1.5, and 2, 2. And so if I connect all of these, not too bad, I should get a graph like that. And then remember at the end, we want to just go ahead and drop a perpendicular. Okay. And so if we graph this function and divide it in the interval into 4 equal sections, that means that I'm going to be dividing it into 1, 2, 3, and 4 intersections, okay? Now, we don't always use 4, but because we're calculating these by hand, I just didn't want us to do way more work. Rather, I wanted us to focus on the process here, okay? So we've graphed it. Now, let's think about the approximations that we've learned so far. We've got an LRAM, an RRAM, and an MRAM, and then we have the trapezoidal approximation. So if I think about the LRAM, that would mean, and let's pick some good colors here. If I were going to do the LRAM, that would mean I would pick this, 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 and this y value to draw my rectangles. On the flip side, if I chose RRAM, I would be picking this one, this one, this one, and this one. So some of them are the same, but one of them is different. If I were going to pick an MRAM one, I would be splitting the difference, so I'd pick a y value like here, and here, and here, and here, so like halfway. And then if I wanted to do the trapezoidal, okay, and let's zoom back up to this example, the trapezoidal means I pick the one of the endpoints counts once, the last one counts once, but everything in the middle counts twice. So that would get me this one counts once, this one counts once, and then twice, twice, twice. The other difference about the trapezoidal is that the top is slanted. Okay. So let's look at parts B, C, and D. It says which approximation would give an overestimate, an underestimate, or an exact answer. Now, I'm going to go ahead and start with the exact answer, because if I draw my trapezoids and the tops are slanted, I'm going to get exactly this function. So the trapezoidal one approximation in this particular case will give me an exact answer. Okay, and that's because it's a linear function and the top of it is perfectly diagonal. If it's not a linear function, that might not be true. Okay, so which approximation will give me an overestimate? Well, if I start with the orange points, that would give me sort of this flat line here, and this one here, and this one here, and this one here. So that one actually seems like an underestimate. So I could say that LRAM gives me an underestimate. But if I think about the right rectangular approximation, that one would be like here, 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 and here. And so that one would be an overestimate. Now we're going to leave MRAM out of this because it's really hard to tell with MRAM if it's just perfectly above or below. Okay, but for those of you who want to explore that a little bit more, I will tell you that MRAM in this case only, because it's linear, happens to be an exact approximation. Okay? All right, now part E, and this is maybe what you were hoping we would do for that last question. Like, enough with the approximating. How do we find an exact area? So it turns out that we can use antiderivatives to find the exact area between the curve and the x-axis. So we've got the area from 0 to 2 of x to the first power dx. And if I think about x as a derivative, and I take my antiderivative, okay, so it'd be important that you've seen the 4.10 videos. If I want to find the antiderivative of x squared, or x, I know that the power used to be 2, because 1 plus 1 gives me 2. And then I take the reciprocal of 2 to get me the coefficient, which is 1/2. Now, I know that we said, hey, you need to put that plus c on the end when it says general antiderivative. But if I tell you where to start and where to finish, then there is no plus c. Instead, we draw a bar at the end. We put our starting point at the bottom. We put our ending point at the top. And 2 and 0. And then we plug in the top number, and then we subtract if we plug in the bottom number. So that looks like this. 1/2 2 squared minus 1/2 0 squared. And this 2 comes from this 2. And this 0 comes from this 0. Okay, so this is where you stop counting the area, and this is where you start counting the area. This order is super, super important. If you are someone who memorized quotient rule the wrong way, don't make the same mistake here, okay? The order is important. It has to be where you stop minus where you start. And let's calculate that out. I'll get 1/2 times 4 minus 1/2 times 0 squared is 0. And so this gives me 2 minus 0, or an area of 2, okay? So if I approximated using the trapezoid or the MRAM, I would get 2. But if I did RRAM, I would get a number bigger than 2. If I did LRAM, I would get a number less than 2, okay? So let's go ahead and try one more example like this. So here we have another finding the area question. We want to start at 1 this time, and we want to end at 2, and the function that we're interested in is 1/x. So I'm going to go ahead and graph that 1/x. Let's use a little XY table to get us started. So I want to start at 1. If I plug 1 into 1/x, I get 1. So 1/1, or 1 comma 1 is one of the points. The last point I want to plug in is going to be 2. So 1/2 is 1/2. So 2 1/2. Okay. But I want to take this area between 1 and 2, and I want to cut that into 4 equal sections. So each section is only going to be 0.25 big. Okay, so I've got 1.25, 1.5, and 1.75. Now, if you're interested in how to find that, there is a formula. You can say b minus a over n. B is your top number in the integral, minus a is your bottom number in the integral, divided by how many subsections you want. And you'll get 2 minus 1 is 1 over 4, or each division will be a quarter of a unit big. So let's get some numbers for this. 1 divided by 1.25 will give us 0.8. 1 divided by 1.5 will give us 2/3. And 1 divided by 1.75 will give us 0.5714. So I'm going to approximate this to the best of my ability on the graph. I know that at 1.5 it's 2/3, so 2/3 is maybe about here. At 1.25 it's about 0.8, and at 1.75 it's a little bit more than half. And so I've kind of got like, wow, that was terrible. I hope yours is better. You've kind of got a small piece of the curve like that. And we want to drop the perpendiculars at our endpoints, okay? And then we're going to draw those 4 divisions. Okay. So, same questions. Which ones would give you an overestimate, underestimate, or an exact answer? Now, in this case, I would say that because the top is kind of curved, no approximation will give an exact answer. Okay? So because the top is curved, I can't say that LRAM or RRAM or MRAM is actually going to be perfect. But I can think about an overestimate versus an underestimate. So we used red for right and orange for left, so let's do that again. So red for right, which would mean this one, this one, this one, and this one. And orange for left, which would mean I would pick this y value, this one, and that one. So I can tell by looking at this, if I use my left approximation, that is going to give me an area that is an overestimate, because all of those rectangles are taller than the black curve. Using that same kind of reasoning, I realize that the red rectangles, or the right ones, are all going to be below the curve. And so I'm not going to get an overestimate, I'm going to get an underestimate. Okay? So to wrap up this video, let's go ahead and use antiderivatives to find the exact value of the area between the curve and the x-axis. So the integral from 1 to 2 of 1 over x dx. The integral for 1 over x, what function has the derivative of 1 over x? And it is natural log x. Now there's no plus c because I have a stopping point and a starting point. So I start at 1, I stop at 2. And to put those into my equation, I have natural log of the stopping point minus natural log of the ending point. Now this happens to be 0, so I can say my exact answer is natural log of 2. Okay? So that's where we're going to stop for this part 4 of the video. Come back for part 5, and I'll see you there.